Well, while everyone's joining, I'll go ahead and get started. First of all, thank you everyone for joining us today. We're excited to have you guys here and excited to talk to you about what we've been working on in terms of putting together a whole brand new combined license application structure. The intent of what we want to talk about today is really to share some of the background that went into it. Basically over the course of the last really over 2 years now, we've been working internally and with the NRC to come up with a new application structure that's really well suited for advanced reactors and some of the unique aspects that they bring to the table, frankly, and some of the differences that are inherent to them compared to the large light water existing fleet we have. And therefore, against difference from the precedent of legacy application submissions. We started that work about 2 years ago, looking at it from structuring it. And one of the things that stood out to us in the process as we developed a pilot application that we submitted to the NRC in late 2019, all the way through then taking feedback from that process to developing a full combined license application that we submitted earlier this year, is effectively in the 2018 pilot, one of the things that stood out to us was the fact that everything had been really focused on the safety aspects of the plant. And one of the things that we realized was there's a lot of tie over and carryover into the other aspects of the application, from environmental to siting and so forth. And so we set about really structuring a new structure that was really built fundamentally based in the regulations themselves. And what we want to do today is let folks know kind of how that structure looks, some of the things we intentionally, like the methodology, if you will, behind it, how we came up with that approach, and ultimately, hopefully, it's something that's useful for everyone, right? Our view is advanced reactors are going to be one of the most important tools we have in humanity's toolbox for climate change. We need to build, frankly, as many of them as we possibly can. So everything we can do to help move the ball forward for what we're doing, but also for what everyone else is doing, is really the intent here. And ideally, some of the lessons learned from what we've done will help everyone else. And hopefully it really shows that there can be more transformative and, I'd say, revolutionary steps taken towards licensing and deploying advanced reactor technologies beyond just the incremental changes sometimes that I think might be something that could really slow us down in what we're trying to do, broadly speaking. So with that, I'll go ahead and hand it off to Caroline, who'll be talking. We'll be having questions and answers at the end. So if you guys have some Q&A, please feel free to share them in the Q&A box that's on the Zoom link or on your Zoom window. We already have actually a decent number of questions, so we'll probably have more than we can answer, but we'll do the best we can to answer as many as we can at the end. Bonita will be the one who starts asking those questions after we wrap this up. And then between Caroline, myself, and Alex Renner, our Director of Licensing, we'll be answering them. So with that, Caroline, go ahead and take it away.
Okay, hopefully everyone can see the screen. We just started sharing the screen, so that should be good. Yeah, thanks, Jake, for kicking that off. There's a lot to get into. I think we're going to try to get the content within an hour and then stay a little after for questions. If we end a little early, we may have a little extra time for questions as well. So we'll go ahead and get started. So yeah, like Jake said, we're going to hopefully provide you in this quick hour a glimpse into how we formulate our application, what it looks like, and how it compares with the history of applications. So just an introduction, Oklo is developing clean energy generation. You may have seen our launch of the Aurora. That's what the application is about. We're doing that mostly because we're motivated to solve energy issues within our world, both on the pollution side, but also on the human side, providing energy that is clean and reliable to people in remote areas. The Aurora combined license application was the first ever for advanced fission and the first received by the NRC in over a decade. The application is different from traditional applications in a number of ways that we'd like to talk to you about. And some of those were necessary, we believe, in order to bring a new technology, a new operating model, and honestly, a new safety to reality. A little bit about Oklo. So we've raised the first ever modern venture-led Series A for a fission company. We began formal pre-application work with the NRC in 2016. We were granted a site use permit from the DOE for the INL site in 2019. We were also selected to demonstrate reuse of fuel material with the INL in 2019. And with that, we were able to submit our first combined license application to the NRC this year. So we're designing clean energy plants for microgrids with advanced fission and solar. So several places you may have seen us in. We were recently featured in Architectural Digest, Wired, Goldman Sachs podcasts and panels, Hyperallergic, VentureBeat, and Crunchbase, among other publications, especially industry publications. So why fission? Why were we motivated to do this? Well, for one, it's reliable. This is somewhat older, dated data, but the capacity factors have actually only increased since then. But you can see that nuclear is near the top of capacity factor. What capacity factor means is percentage of uptime as far as producing electricity and at full power. And so you can see how that kind of compares. So reliability is really important for remote areas that we're looking to serve. It's also clean. Nuclear, may not realize, is providing majority of US emission-free electricity right now and has for some time. Also, one interesting factor is the actual life cycle carbon footprint of energy sources. Because it's so energy dense, you can see that that plays a major factor into how the life cycle emissions can be calculated. Those actually include from mining, and you can see kind of in the fine print down on the right-hand side, raw material all the way through disposal. When you have something that's so incredibly energy dense, it really sharpens and lowers the total life cycle carbon footprint. So to get into that energy density, you can see here one chart that we've made that shows the differences in the amount of materials needed to produce power with different energy sources. And advanced fission is near the bottom of that. And we really believe that's part of the promise of why we were interested in fission, in advanced fission in particular. That actually plays out in how much land use is required. Here you can see a great infographic that talks about the amount of land use for different types of clean energy sources. And there's a couple more pictures I like to show. There's this great XKCD cartoon that I think probably a lot of people have seen, but it gives a little bit of an fun illustration of how much energy density there is in uranium versus many other chemical processes and combustion processes. So energy density is absolutely incredible, and that should lead to lower costs and lower carbon footprints for everyone. So the Aurora. The Aurora is our first product that we've launched, and it produces between 1 and 2 megawatts electric. There's 20 years between refueling, and actually our license that we submitted was for a 20-year license. The Aurora is a powerhouse that includes the advanced fission battery itself with solar panels on top. And the Aurora can utilize used material. So I mentioned we were selected for an opportunity with INL to demonstrate reuse of fuel material. That's an exciting potential for fast fission reactors, and something that we're excited to potentially even demonstrate with our very first plant. Each unit saves 1 million tons of CO2 over its lifetime compared with the diesel generator alternative, which is in most places the only reliable alternative they have, especially in the dark winter months in Alaska, for instance. There's a broad array of applications that can use this kind of power. They range from campuses, off-grid, remote communities, data centers, hospitals, you name it. We've been approached by resorts, things like that, and even developing areas in the developing world to be able to have this power in small chunks instead of having to build a gigawatt-sized plant is something more in the realm for these developing areas that want to get more reliable power to grow their economy. And we believe as costs drop, microgrid plants will be useful for increasing markets and uses. There's also, we have actually we operate with small power density. So a few things about the Aurora and how it's different. So to start off, it's incredibly important to actually set the stage for understanding how different this is from power plants that people are used to seeing and the regulators used to seeing. The Aurora produces 4 megawatts thermal, which is far smaller than obviously any commercial reactor, and even smaller than some research reactors. For one comparison that we've used and we've actually put in our application, the entire Aurora core produces about 1/4 of the power that one fuel assembly at Diablo Canyon produces. And it has comparatively about 100 times the proportional mass a fuel cladding and structural material in comparison to kind of distribute that heat load over. So it's got kind of that characteristic on safety as well. It has a small decay heat production, so nuclear is unique among power sources. Even after you turn it off, it keeps producing heat. That can be one of the challenges for safety, is managing that heat and making sure even after the reactor shut down that you're appropriately transferring that heat so there's no melting. The lower power of the Aurora actually leads also to low decay heat production. One example, just to put in perspective, is after 1 day, it produces about the same amount of power as like a riding lawnmower, and more specifically, this one that I chose for this slide. We're using metal fuel. There's a lot of reasons why we started with that as a premise. It actually has decades of operational data from the IFR program. Many people may not have even heard, even nuclear engineers have not heard about this program that actually operated a fast reactor with metal fuel for 30 years. So that was an incredible wealth of data that we wanted to make use of, as well as incredible safety record. It keeps fission products within the metal up to a certain burn. So one nice thing about metal fuel is it's very resistant to cracking and chipping, and it actually itself acts almost like a. So that is important for safety and making sure that there's no doses being released. So, again, it's easy to relatively manufacture. Pretty resilient to different types of manufacturing methods. And actually, Oklo was able to work with INL through a GAIN grant to fabricate fuel prototypes in 2016. So we've actually seen that in action. It has high thermal conductivity and low specific heat. So we're able to make use of peak fuel temperatures and low stored energy, and it's easier to dissipate heat from the fuel. Overall, the design is incredibly simple. There's no pumps or valves, etc., in the core or primary heat transport from the core. There's no complex flow loops. Shutdown rods themselves are gravity aided, and there's no active control rods needed to control power output during operation. It's passive, and the heat transport is passive, and it's very efficient. We call heat pipes sometimes thermal superconductors. Sometimes people think that's a weird term, but when you consider what the equivalent thermal conductivity is on the order of 1,000,000 watts per meters Kelvin, that's really essentially how it looks in modeling and in operation. It doesn't require any chemistry control, similar to a lot of flow loops people are used to seeing. It's not pressurized. In fact, it's actually slightly subatmospheric pressure. So if anything were to break, it wouldn't actually explode open. It would maybe suck a little bit of air in. It also doesn't require any makeup inventories. Complex systems that are required for makeup inventories exist in a lot of existing reactors, but those aren't required here. So you have many independent pathways for heat transport, each of which being passive and very, very simple. One thing to say too on that simplicity point, one thing that people are used to seeing for large light water reactors is on the order of tens of thousands or more individual parts. Ours are more on the order of about 100 unique parts, hundreds. So that's just a very different scheme to work under when you're looking at quality assurance, when you're looking at complexity, when you're looking at what could go wrong. It just changes that whole paradigm. So moving on to other Aurora features, we have the entire reactor module and primary heat transport below grade. We believe that's really important for simplicity, safety, and security benefits. We've actually demonstrated that in our application. No offsite power dependence, and actually no human action required for safety at all. And no periodic refueling intervals. So you saw, once every 20 years. And for the life of this license that we're applying for now, there's no refueling required. So a little bit about regulatory background. I won't bore you, but it just helps to get a sense for what existed before and what we were up against, years ago when we were first starting and trying to think of how to engage the regulator. So obviously the Atomic Energy Commission started far before the Nuclear Regulatory Commission, and they actually had the dual roles of both promoting and regulating nuclear energy. It was decided that those should be separate roles. And so in 1975, that was split into basically DOE and the Nuclear Regulatory Commission. I'll be using the acronym NRC throughout this presentation. So if you hear that, that's what I'm talking about. And the Nuclear Regulatory Commission, actually some people don't realize, but some of their very first work was actually on a sodium fast reactor. And so they have had a pretty long history, decades now, of looking at these, but there is some dusting off and some rebuilding of expertise that's been going on, extensive work going on between DOE, the labs, the NRC, and the industry to get them back up to speed, being ready to look at and actually accept an application for a non-light water reactor. Yes, so they had that experience, but we're working on it now. And in the meantime, though, since the Nuclear Regulatory Commission began, they continued to develop this large body of regulation and regulatory guidance in particular, mostly based on LWRs, especially the regulatory guidance. Guidance is actually, regulatory documents that help interpret the actual regulations for applicants as well as for the regulator themselves to interpret how they should enforce the regulations. So for every regulation, there's an incredible amount of guidance in general. So that's kind of the bigger bulk of things, and that's really where things became very technology specific into light water reactors on average. And one thing to remember is actually no license initially submitted to the NRC has yet begun operations. So since 1975, there have been things that were started, but all of them began under the AEC. Vogtle would be the first once it starts operations, but this is obviously a trend that should change. We don't believe that the safest power source is one that never starts, especially when the alternatives are so dangerous and can be fossil fuels and polluting and so forth. This is just a little context on the early days of regulation and nuclear energy for peaceful uses. It's called the atomic age for a reason. For a period of time, there's kind of these regulations that actually were simplified in order to demonstrate new reactor types, and that is still referenced in Class 04 licenses in the regulations. And in fact, the very first private commercial plant to put power on the grid, privately owned and operated, was actually a microreactor. It was 5 megawatts electric, produced 40,000 megawatt hours in California, actually, not very far from where we're based here at Oklo. In fact, you can see there on the screen a picture of Jake and I in front of it. It's at Vallecitos near Pleasanton, California, for those that are familiar. So microreactors are really very new, but they haven't been done very much more recently. We believe that more recent trends in terms of distribution of grids and the rise of microgrids and the rise of concern about pollution and climate change all come together to make this a really important time to look back at that history and to look at microreactors. I added in here a quote from JFK. It was actually his last recorded speech, and he talked about using fission technology for peaceful power, peaceful purposes and power. So we have some pictures actually at our office of JFK at that location at Hanford where he gave that speech. It's kind of an inspiration for us personally, and wanted to share it with you as well. So the NRC has 2 different licensing pathways, broadly speaking, Part 50 and Part 52. So Part 50 is considered a Class 1-3 license, so it's different than that historical demonstration license. It's different from research reactor licenses and other things. Usually what they're referring to is Chapter 10 of the Code of Federal Regulations, Part 50. So they just say Part 50 licensing. New plants had to get a construction license and an operating license separately. What that led to was there was a stream of plants that got the construction license built and then weren't able to get their operations license and basically were never operated. So this led to large regulatory risk. It can be used today, and in fact some non-LWR companies are looking at using it, but it raised some questions especially in the 80s, 90s, and early 2000s, as far as there has to be a better way to kind of do both pathways at once and not incur that regulatory risk that's involved in getting the operations license separately. So PAR 52 is the second main path, and that was basically only just began being used in the mid-2000s formally. It's called a combined license, so it allows for licensing, construction, and operations simultaneously. There are actually a lot of different paths to reach the COL, and I think that's where a lot of confusion comes in. So you can do a design certification first. That is actually a rulemaking, and then pair that with other information to submit in your full COLA, so combined operating license, combined license application, so it's called COLA, that leads to a COL. You can also get a bunch of different standard design approvals, so this can be large subsets. Pair those together into a COLA to get your COL. There's actually also a manufacturing license that already exists, and actually that was exercised in the 80s, but it hasn't been used to completion as far as having reactors manufactured in a plant. But interestingly, it does exist and has existed for a while. It just hasn't been very much used. So you can use the manufacturing license along with other information to make a COLA and get a COL. You can do a direct, or what we've been calling a custom COL, COLA, and to get a COL. Also, one thing that is used extensively is just using topical reports, which give you SERs that can be used to augment any of the paths that we just described. In essence, the standard design approval is very similar to topical report. It results in an SER. It can be on a major topic or a major system area, and so you can kind of do staging in those ways. So there's a lot of different ways to get to the end goal. And right now, the main exercise path is doing a design cert followed by a COL, and AP 1000 did that, and NuScale is pursuing their design certification right now. So what are we doing at Oklo now that you have this background? So we're pursuing a custom COL. So going straight to this COLA, submitted the COLA, and not doing a design certification first. One of the reasons is because we realize, with your first of a kind, you're going to learn things. Do you really want to go through the strenuous process of doing a full rulemaking on a design that has to have a certain level of design finality, and you're codifying it into regulations permanently before you've built your first one? That's a big part of it. And also, we didn't see the benefit of doing staging. Our business model is a little different. We're not planning on getting a design cert and selling it to a utility who then have to do all the operations and building and so forth. We plan to build, own, and operate, and we really care about all of those phases of the process at once. We think that leads to a really good design process as well. If you're really thinking about, okay, I'm not just designing this, I also have to operate. I also have to think about these other aspects of building and manufacturing and operating. It really leads to a different design process. We'll talk a little bit more about that as we get a little further. So there's several things we're doing differently with our application. One of which is how quality assurance is done. At first glance, our quality assurance program description, long name, QAPD, was just issued a draft SER. We're working through that process with the NRC now. It looks largely like the NEI template or many other QAPDs you may have seen, but the way we do QA is very important to us, and we've been doing some very unique things with that. We may be a subject of a different webinar, but that's one of the items. The NRC actually did some other things on their management side with us that we really believe has led to a great outcome. One of which was that we had a core team assigned to our pre-application time, as well as carried into our application review. We're still in the stage of, we submitted it, we're in acceptance review time. But having that core team have some continuity, we're not talking to a different group of 50 people each time we have a meeting. That really helps for planning purposes, for not having to rehash old things, hopefully, and really allows them to get to know us and us to get to know them, to make planning and budgeting much more effective and information transfer. They also were willing to engage with us on a licensing project plan since early in our pre-application time, and that allowed us to kind of come together once a quarter and say, okay, here's the meetings we were thinking, here's the reports we were thinking, here's the rough timelines. They could allocate manpower. We could have some planning capabilities on our side as far as budgeting as well. So it was really a useful platform to do that. Since the time we started using it, the NEI has also codified a regulatory engagement planning guidance for pre-applicants to use. So we point you to that as kind of a template, or some of ours are public and able to be seen. So that was also a useful process. Lastly, just having a extremely simple safe design in comparison to what the NRC is used to seeing really means less safety related, what's called safety related parts and issues. And I put that in quotes because for people who aren't deep in regulations or regulatory work, you may not realize that safety related, important to safety, safety significant, all are terms that actually have very specific meanings and trigger different things. And safety related being the most significant, and it's really what leads into different quality assurance procedures and so forth. So when you can really make the safety inherent, you can kind of whittle down on things that have to have the most rigorous and the most expensive types of quality assurance, and you can do it in novel ways. So in novel application, we had to frame the unique safety case for a non-LWR, and where do we start? The challenge is that, there's decades of regulatory guidance for plants. Costs and requirements have increased over decades, and some of the requirements and the costs would literally make advanced reactors, but especially very small plants, essentially a non-starter. And we can get into some of those items off the top of your head. You can probably think of several. Operations, expectations for operations and security are just the start. You can't have a 1 megawatt plant with 50 security guards and make it economical. It just can't happen. So that's one example. One other thing that people always talk about risk informed, but one thing that does lead to a challenge is you don't have, it can be very useful with appropriate treatment of it. It can't look exactly like a light water reactor or PRA because those have literally thousands of reactor years of data over many decades. For some of these are the first of kind to be built. You don't have that kind of data. You can definitely make educated guesses and utilize different types of data from different industries or even from previous operating advanced reactors, but you don't have quite that wealth of data. So there has to be that understanding, and that can be a challenge if you're fully risk-based. And I think that's why many have looked at being risk-informed, not just risk-based. So one thing we really dug into was the idea of a maximum credible accident. It in fact had its roots of conceptual use since before there was even a regulatory framework. And there's some interesting parallels, right, between this new time of using advanced fission technologies and the earliest days of using fission at all for power before LWRs became the standard. They were, digging through how can we look at what's the worst that can happen and how we prevent it and make sure that we protect the public. And so there's this idea of a maximum credible accident. The idea was the worst credible accident caused by any single event or any single failure. So it's more deterministic than it is risk-informed, but it's very interesting. We at Oklo actually performed a broad review and analysis of all kinds of events, actually utilizing the existing light water reactor guidance, but it has a lot of insight for how events can progress. Historical non-LWR events and PRAs, and events particular to this design and this type, reactor type. Our reliance on this worst case scenario kind of removes some of the uncertainties that can be inherent in reliance only on risk analysis, especially for a first of kind. But we were able to utilize insights from probabilistic analysis in order to ensure that we have defense in depth in our application. Defense in depth is a term used to make sure that you're not relying on any one thing to ensure that you're very safe. So usually in nuclear terminology or regulation, the idea is many redundancies inherent into your safety. So that's one of the things we utilize was risk analysis to do that. Further precedent for our safety case and the kinds of things we had in our application is actually taken from or can be referred to the precedent from research reactors, right? So we're larger than some, but smaller than other research reactors that have operated. Just because we reduce power, does that mean we should have totally different requirements, right? So that's one of the bases also for how we looked at doing safety analysis. So we started using this term safety case. I think it's become a broad usage. How do we present this case to the NRC, and how do we best communicate that and most effectively communicate that to the NRC and to the public, and best back it up. The real safety case comes back to several inherent features of the design, some of which we've already talked about. So I'll just run through them. Small size, low power density of it is actually lower than a lot of the, for those that are familiar, the NG case examples. Low fuel burnup, small inventory of fuel, and limited possibilities for dose. So with such a simple design, there's not as many things that can go wrong in quite the same ways. Low decay heat term, so it's easier to manage decay heat. Inherent reactivity feedbacks, high thermal conductivity, and not having a pressurized system, which limits the driving forces for release. So we take this unique safety case, and how do we put it into a structure based on existing regulatory requirements? Fundamentally, our application is built from the regulations for COLA application content as it is in the Code of Federal Regulations. So that's in 52, Part 77, Part 52, Chapter 77, 79, and 80. And this final COLA structure has also used unique methods to track key assumptions or key parameters that we want to guarantee by certain commitments, programmatic controls, and so forth, to really make sure that all of the safety and assumptions are directly tied to everything that we're doing before we start the reactor, and even in operations to continue to assure those things. So we think we've come up with a really interesting and unique way of doing that. So what are the COLA requirements right now? They're, like I mentioned, in 52, 77, 80. And our application follows those structures. There are obviously some that are directly referencing LWRs or PWRs, BWRs. And if it doesn't apply, or it does apply, but we had an exemption related to it, that ended up falling out into the Part 5 of our COLA, which is non-applicability to requested exemptions. So here are all the parts all together. You can see them, and actually they're all available for download. And you can reference our social media for the link. It's actually pretty easy to remember. It's bit.ly, so bit.ly/Aurora Cola, where A and in the Aurora and Cola are capitalized. So you can just go directly to our entire application. Is available there, as well as on the NRC website. So Part 1 is company information and financial requirements. Part 2 is the FSAR, which is what many people find very interesting. But also equally interesting, potentially, to the public in particular, is the environmental report. Tech specs is one of the things that you can use to continue to assure safety as the plant is operating. Non-applicabilities and requested exemptions, Part 5 as mentioned. And then there's proposed license conditions before you can get the license, and then enclosure. So there's a number of programs and plans that ended up being in the enclosure portion. I'll start with talking about the environmental report. And so as you can imagine, with such a small plant, we also have a very small footprint. And in fact, we only have anticipated to have about 2 people on site at any given time. So it's almost like a large house with 2 people living in it as far as the environmental impact. So there's only one building of approximately 4,500 square feet land area, and so that's the projected, kind of site footprint. We don't have any water requirements for cooling for any industrial use or reactor or safety use, so there's only incidental water usage for the 2 people that are on site. And like I mentioned, we have a small workforce, so there's only the 2 people. And all throughout the production of our environmental report, we really had in mind that this should look differently for something that's roughly 500 times smaller, at least in thermal output, from a typical plant that they've done environmental reports for. So how do we right size that but still contain the information required by the regulations, as well as the information necessary for the staff to do their reviews? We also, given current interests and current congressional requirements on the NRC, we did try to make a structure that lends itself to actually using it for a generic environmental impact statement. And so that's the acronym for that would be GEIS. And the idea is that you can, if it's the same plant and certain things are the same no matter where you cite it, you could potentially get a GEIS. And given that certain parameters are the same across different sites, you don't have to redo the environmental report for each site unless there's certain extenuating circumstances or unique characteristics. So we did really structure it like that, and if you read through it, you might find that quite interesting to take a look at that. The organization, this is where it becomes a little bit of an eye chart, but you can see each regulation, and really the environmental ones are in Part 51, how tight. And actually our environmental, you know, commercial plants, and yet we feel like we made sure that address each regulation. So there's not regulations that we're not addressing in either this chapter or in an exemption. It's a bit more meaty to get into the fundamental safety analysis report. This is definitely the largest portion of our application, and so I'm going to try to run through that as we're wrapping up here. Aspects. As mentioned before, the FSAR contents really followed the Part 52, Part 79. And you can see the list of them here. So certain sections kind of fell out or were condensed or reorganized, but largely it is actually still in order of what 5279 lays out those requirements for. Our largest chapters are Chapter 2, well, 1, 2, and 5. So 1 is the site information, 2 is describing all of the system structures and components, and then Part 5 is all of our transient analysis. Really, our safety analysis lives in largely in Chapter 5. Other important sections are seismic and earthquake criteria, so you can see that in Chapter 7, and a lot of operational plans as you get further down the numbers. So they're all honestly interesting, but many of the descriptions, like training program description, so forth, are just brief descriptions of the program, while the program itself was submitted as an enclosure to the application. So this basically says what I just said. There's a number of operational plans that are really required to be submitted in a COLA. So this is different from a design certification. It is, in a sense, more extensive. You have to be thinking about those things. How you're going to do emergency planning, physical security planning, radiation protection programs, and training programs I mentioned before, etc. So these plan documents are included in the enclosure portion, and I think each one of them we tried to, again, be creative and address each of the regulatory requirements for those kinds of topics. Briefly, you know, how Oklo did our design and analysis is very iterative. And so many times when people say, oh, well, what's your TRL level? In a sense, you could relatively instantaneously go from low TRL to higher TRL because we have essentially like a digital twin system here at our headquarters that we utilize to very quickly modify parameters and very quickly couple in safety analyses and even our PRA. So we were able to do dynamic PRA analysis all at once. So it's very exciting. It's such a simple, tightly coupled system. You can really do really interesting things. But of course, you know, as we've gone through the years, things iterate. So you think about the design, what do customers want? what do those lead as far as high-level requirements, then doing safety analysis on it and honing the design and so forth. As we got into more and more event types and analyzed them, different tweaks would have to be made. But one of the things, like I mentioned before, is as we do that, basically key parameters fall out, certain assumptions that have to be made, or certain key physical characteristics that have to exist. We wanted to codify those, even if it's like metal is metal. And I'm being a little facetious, but you're assuming a certain physical property for that material. And those can change with temperature. They can change with burn up, and they can change with swelling and so forth. So even such assumptions do need to be codified, and certain design changes can change all of those different things. So we utilize unique online systems to manage that, but we also codified certain of those assumptions as design bases. So we really realized, okay, for our analyses to hold water, these things must hold true. And I'll give a few examples of how those look. The design bases lead to design commitments in order to ensure those design bases, and then certain programmatic controls that are used to ensure that the analysis actually meets how it's built and how it performs. So here you can see kind of a flow chart. So the design bases are the characteristics of the system that ensure safe operation. Design commitments are specific commitments made to ensure that design basis is met. The programmatic controls are administrative or other certain programs that are used in certain ways to follow through on that. So it'll make more sense once I show you an example. So you can see those in kind of a different level. So as far as programmatic controls, you can see each one has kind of an acronym behind it, and you'll see where that plays in. Different systems, as well as different programmatic controls, have their own acronyms and are able to be tracked in certain ways. Quality assurance program is one way. Pre-operational tests, so before we start operating, making sure certain things look the way they're supposed to. Startup tests, inspections, tests, and analysis acceptance criteria. So usually almost always people just say ITAC and don't even remember what it stands for, but there it is. And then technical specifications, which go on through the life of the plant. All of these things can tie back and make sure that the things that we're assuming now are actually happening in performance. So within the application, there are periodic gray boxes that look like this, although with the dark gray background, it doesn't look so gray, it looks more white. But you can see it'll have really call out within these gray boxes. So we want to make sure, how do we communicate and really highlight the things that are most essential? And our team really came up with this amazing plan to really call it out with these gray boxes and to use these acronyms to track it. So design basis might look like DB for design basis. RXS is an example for the reactor system. So we use RXS for that, and then a number. So there might be design basis, RXS number 1. And then that really leads to an important characteristic of the reactor system. And then, it gives a little description within that box of what that's supposed to be. And then it also describes any design commitments or programmatic controls that flow out of that, which you can refer to in different sections and really find, do a Control F and find those things where they fall out. But a brief description is given within each of those gray boxes that you might see. Different commitments will flow out of that, and so it uses the same numbering but adds a letter, so like you see there. And then, here's some other examples like POT.RXS.O1.A. That would be a pre-operational test. So POT, like you saw on the previous slide, and so forth. So SUT, ITAC, tech specs, and so on. And I know we don't have enough time to really dig into this too much with case examples here, but I want to describe this so you can see that I think one thing we've seen as lessons learned from so many reactors designs and vendors through the ages is, how do you really track these things, and how do you track how changes propagate as far as affecting either really important issues or not important issues, and how do you suss that out? And we think that this system really helps with isolating those and assuring those. So in conclusion, the combined license application was the first ever for advanced fission, first received by the NRC in in over a decade of any type. The application is very different and basically had to be in a number of ways. The whole structure had to be different for an LWR while meeting existing regulations. The content had to be right-sized and also, to ensure that we're meeting regulations as opposed to precedent or guidance that was really geared toward light water reactors. So we had to really come up with a new structure, consider the content to be right-sized, do safety assurance in a more holistic and integrated way was something that was important to us. And the environmental report was also very different and structured to make use of a potential GEIS. And the environmental report was also different in a way I didn't really mention so much earlier, which is actually mentioning environmental benefits or trade-offs of a plant. So if your alternative is diesel or plants that use much, much more land area, there can be definite environmental trade-offs. So we tried to actually include that in our environmental report, which is also a different perspective. So with that, I guess we did leave a good amount of time for questions. I guess we'll see. I'll turn it back over to Jake, who can talk about what questions we might answer, and Bonita, who will be reading them off.
Sounds good. Awesome. Thanks, Caroline. Thank you so much. And thanks for everyone who joined. We've gotten a lot of questions, so we'll go ahead and just try to get through some of these and try to be able to at least archive some as well. So Bonita is going to be able to then throw some questions out to us, and then we can start answering them. And again, I'll be able to chime in, and then Caroline as well, and then also Alex, who's our Director of Licensing. So fire away, Bonita.
Thanks, Jake. Thanks, Caroline. Hi, everyone. I'm Bonita Chan. I'm the Director of Marketing and External Relations here at Oklo. Thank you for all your questions. We got some great ones. So let's get started. So the first one is, Caroline, you mentioned that the Aurora having hundreds of unique parts, while traditional reactors of many more. Could you expand on how this design characteristics is expected to improve safety / regulatory approval as well as overall cost reductions?
About that? Yeah, I'll actually turn that over to Alex to start. So I know Jake introduced her at the very beginning, but Alex is our Director of Licensing and really led a lot of this work. And so I'll let her begin, and Jake and I might add on to that as well.
Yeah, hi. Yeah, my name is Alex. I've been leading kind of this approach, and yeah, I'm happy to take a first stab at this question. There's obviously quite a few parts to it. In terms of how do we have so few components? Well, obviously this plant is 1/1000th of what's been previously licensed by the NRC. So of course there's much more simplification. A lot of the components are not active, and so therefore you don't have the same kind of backup systems or redundancies that would be needed for safety. So essentially the approach that we took here is how can we really minimize the amount of parts that the regulators really need to pay attention to in order to be able to more directly focus the application and subsequent review.
Thanks, Alex. Bonita, do you have another one?
Yes. So another question here is, your plant design it would be very welcoming to community members. Would it be possible to have your building be used for multiple roles, like a study hall, on a campus, office building, restaurant? I'm just curious about the limits, if there are any, that the building can be used for.
I'll start with that. Yeah, our footprint, it was really important to us to be able to have a footprint where there weren't fences and armed guards unnecessarily. The building itself essentially acts as a fence, and this is not entirely different from some research reactors. But inside of the building, there are different access controls and essentially fencing, and even outside there's certain security barriers, but those don't prohibit people from being on site. But there are prohibitions, of course, within the building as far as access. But the interesting thing about that is that the land around it can be potentially used for other community resources, and that's something we are excited about, and have started initial conversations with different communities about how that could look. And one of the things that we talked about when we launched the Aurora is that the solar panels on the side actually are able to have customizable art for local communities. So it's kind of cool and hopefully ties in local aspects, even as the building will be the same at different sites, or at least as we're anticipating, and also has certain functionality to the building that I could get into. But suffice to say, we wanted to take on local flavor and have kind of this nice area for people to visit. Actually, many existing plants, even much larger, much different, exclusion boundaries and so forth, actually have nature preserves and different things that people can visit, visitor centers. And that's definitely something we'd like to continue the precedent on, but also do it in different ways where we can have co-located buildings and so forth. There are some interesting factors around that, but our site footprint is basically the building, so it does enable more of that than otherwise.
Great, thank you. I hope that answered your question. And our third question is, does Oklo have comments on the proposed regulatory guide for the modernized emergency planning zones? Will that regulatory guide be directly applicable to Aurora or perhaps future larger Oklo reactors?
I think that'd be a good one for Alex to hit on first.
Yeah, definitely. That's a good question, and I appreciate the level of detail with it. One thing I will note is to do that. There's really no part of it that is redacted. So you can kind of, depending on how deep you want to see that comparison, that's something that is available. In terms of the reg guide and the question there, there's a lot that we drew on from that reg guide, but of course this facility is even smaller than even the kind of initial intent of that reg guide. So although I would say we're utilizing a pretty big portion of the intent behind it, we actually went a little bit further with what we're proposing for our emergency preparedness and the subsequent EPC.
Thanks, Alex. All right, moving on. I think we have time for a few more. So this question is, do you think your approach and structure can extend to advanced reactors that are larger in size, like small advanced reactors, to larger advanced reactors, given the passive safety characteristics of advanced reactor technologies?
Great question. I'll start, and I'm sure Alex will have more to add, or Jake. I think we see this as very extensible, and that's why we're excited to share it with others. There's nothing really inherently about this application that has only to do with our plant, except for of course, the specific items. The structure itself is built from the regulations and current regulatory requirements, which are expected to continue. Even if there is a Part 53, many of these aspects will not be totally redone. For instance, how radiation protection is done. I think it'd be interesting if it is, and in which case, I think hopefully there'd be new structures enabled by that new Part 53. But as long as we're in the structure that we have now, and as long as Part 52 is available, I mean, even when Part 52 is introduced, Part 50 is still available, people could continue to use this format to illustrate meeting the regulations in different ways, and maybe certain parts of it be more, maybe may have some nuances, but the essential structure of it is built from requirements. And so none of that is particular only to Oklo, and we think it could be very interesting to see if it's useful to others.
Thank you, Caroline.
Yeah, and I'll add on just a little bit to what Caroline said. I think the intent with, especially with the structure, as we've mentioned, there are other designs. The Aurora is not the only one, and so the intent is definitely to use that going forward.
That's a great point. We anticipate, we've told people we're working on other designs as well. We directly wanted to be able to use this for other designs. So even within Oklo, we're looking at using it for different types of designs, different sizes, different characteristics. So great point.
Okay, thanks guys. Okay, moving on. What has been the NRC's response to the application so far, given that it may be different than what they've seen before? Also, what is the anticipated timeline for the NRC review?
Yeah, Jake, do you want to lead that off? And I think this would be our last question because we're a little after 1 o'clock Pacific right now. So maybe Jake, you could lead that off and we can start wrapping up.
Sure. I'll just go ahead and say, yeah, I think we've been working with the NRC for a few years now, dating back to 2016 when we started pre-application with them, and we've been working with them to inform them of the design and also what to expect, and then especially over the course of the last 2 years, helping them prepare for a novel application structure. I think in general, they've been really working hard to modernize their approach and prepare to be able to handle something very new. I think we've been pleased with them being able to implement a variety of new, I think, approaches to looking at advanced reactors that build on their experience and lessons learned, including, for example, this integrated core team approach and trying to be very focused on what matters in safety. I think in general, it's useful that we can map everything back to the regulatory side. But as is anything new, everyone has to get used to it. And I think in general, we've been pretty pleased so far in our, ranging from our pre-applications all the way into now our audit review, our acceptance review audit, and mapping out then what that looks like going into the design review space. So, it's definitely, I think, something that we have found that, the interactions have been, I think, pretty productive. They've been pretty useful. We appreciate that they're willing to do new things. There's obviously a sense of importance to this. I think we have to keep that sense of, I think, prioritization and urgency up just across the board, given that, like Caroline said, no license application submitted for a new plant has actually yet been turned on to the NRC, right? All of it was submitted back when it was the AEC. And given the urgency that we have and face to deploy new advanced reactor technologies, it's really important. And I think the imperative is pretty clear that we need to be able to find more efficient pathways to regulate the power plants that actually capture the broad risks of doing it, but honestly also the risks of not doing it. There is a clear societal toll of building fossil instead of nuclear. So I think there's growing awareness on that, and I think a receptiveness to looking at things very differently. But newness always adds some degree of friction, but that's why we do it. And we're happy to hopefully start knocking down different hurdles that both help us, but also help everybody else. I'm not sure if Caroline or Alex want to add anything to that.
I think that's a great summary.
Yeah. And then generally speaking, we'll know a lot more about review schedules and other things that are being anticipated. We've been working with the NRC for some time to map out kind of a review time frame. So we're eager to do that, but we definitely expect things to be significantly quicker than, for example, a bigger plant would be. So we're eager to see how those all map out. I think in general, that's kind of a good way to wrap up some of this. A few points just to make is, this has been recorded and hopefully will be available in the future as we can archive it. As was mentioned, the application is public. I hope folks are able to kind of get a sense of the structure of what we're trying to do and see how that can map back. Sometimes it's kind of granular in depth in some areas when you really dive into the application, but having this overview of why we structured things the way we did, trying to show a direct tie back to regulations helps us, I think, get through the paradigm of trying to honestly build license applications in the structure that applications were developed for over decades for large light water reactors, when in many cases that just doesn't make sense to do. So we hope this is a useful step. Again, the idea here is that people should hopefully draw insights. We want people to be able to use it if it's useful, improve on it if that's what they need to do. And ideally that creates, I think, the right momentum across the industry to, at the end of the day, accelerate the deployment of advanced fission technologies across just the US, but also the world. On that note, I think one aspect that we're excited about is how these things can tie over into international collaborations. One thing we're always a little concerned about is if you have to make decisions by committee, you don't often get to the best places. But ideally, that's not what happens, but instead an approach that looks at, okay, these things are meeting the general intent of the regulations, which is, pretty clear in different countries, and then hopefully that carries some benefit over, especially after it's been vetted and agreed upon by one regulator. So we're excited about that. This also probably won't be the only webinar that Oklo does, or it's just the first. So we'll be keeping you posted as we get into other aspects of what we're doing and other activities that are going on. So again, thank you for everyone and everyone's time. We appreciate it, and look forward to hopefully doing one of these again soon. So thank you all.